Welcome to this webinar that TELLAB is hosting on oil analysis maintenance philosophies. My name is Jan Fogut. I am the business development manager here with TELLAB. I've worked 24 years in oil care, oil maintenance, oil analysis and filtration. And the presenter today is our lab manager, Ashley Mayer. And so I will hand you over to Ashley. Enjoy.
Thank you, Jan, and good morning, everybody. My name is Ashley Mayer. I'm the oil and laboratory manager here at TE Laboratories. I've been in this game since 1996 now, so 26 or 27 years. Mostly based at Wechek, Africa. I also spent some time in the United States working for a company called Noria Corporation, which some of you may have heard of. They're well known in the lubricants game. So with that, I'm going to get started. And what I'll be talking about today, what Jan and I will be talking about today, is the evolution of maintenance philosophies and how oil analysis fits into these different philosophies. First, I'm going to start talking about what oil analysis can show us, and that will help see how it fits into these different types of maintenance. There are three things that oil analysis shows us directly, and it's been called the iron triangle of oil analysis. The first thing is the condition of the fluid. So we're talking about the health of the oil or the grease. We're looking at the health of the base stock, which is what does most of the lubricating. And then we're also looking at the health of the additive package. And the human analogy of that is, we would say, be like the health of our blood. We use the analogy that oil analysis is like a blood sample for your machine. So it'd be the health of your blood, your red blood cell count, your white blood cell count, and antibodies and that sort of thing. The second thing we look at with oil analysis is contamination. This would be like any germs or bacteria that you have in your blood. This is probably the most important part of oil analysis, because 80 to 90% of all lubrication-related failures have contamination as their root cause. That's 80 to 90% of all lubrication-related failures have contamination as their root cause. Fortunately for us, it's probably the easiest part of oil analysis to recognize the contaminants. And we're talking about things like water. In the case of engines, we have soot, we have fuel, we have coolant leaks, dirt, also a very common contaminant, quite easy to recognize. And then the third thing we look at on our oil analysis reports is machine wear. And this would be like any diseases that we have in our body. And as far as the oil sample goes, we're looking at things like the wear metals. And the different metals that we see coming out tell us what parts of the machine is wearing. So those are the three things we look for directly on an oil analysis report. If you look at an oil analysis report, you will see that, and most laboratories do that, that the tests are loosely grouped into these three areas. So there's your machine wear at the top. Contamination is in the middle of the report, and the lubricant condition is at the end of the report. So when we get to our different types of maintenance philosophies that we're going to discuss now, they will direct you to whether you should be concentrating on the wear metals, or whether you should be concentrating on contamination or condition of the report. Before we get into the different maintenance philosophies, I just want to talk about briefly types of failure. Now, there are many different definitions of failures out there. I'm just looking at the ones that pertain to the discussion today. And the first type of failure is what we call a catastrophic failure. And this is where the machine is stopped working completely, and it's due to the fact that the machine has broken down. It's not because nobody switched it on, it's because the machine has broken down. And if we were doing oil analysis with this type of failure, this would obviously be a post-mortem or a failure type of sample. Then you get another type of failure called a predictive failure. Now, a predictive failure is where the asset is still working, but it is in a wear situation. So if we look at our oil analysis report, we will see some red numbers in the wear readings in the top section of that report I was showing you on the previous slide. You will also be generating vibration, and your thermography analyses will be picking up signs of localized overheating. Then you get another type of failure called a proactive failure. Now, a proactive failure where the machine is still working, it hasn't started wearing yet, but conditions exist where wear is going to start happening pretty soon if we don't do something. And here the focus of our oil analysis is going to be on the lubricant condition and lubricant contamination. And this is where we'll be focusing our activities as far as oil analysis goes. Where you're going to start picking up proactive failures with other technology is going to be things like alignment and balancing. So if the shafts are not correctly aligned, you will pick up some type of vibration. It might not have started wearing yet, but if we do our alignment testing, we'll see that something is wrong. And then the last type of failure is a functional failure. Now, this is beyond the scope of this discussion today, but I'll just mention it. A functional failure is when there is absolutely nothing wrong with the machine, but it is not working. It could be a case of the factory is in an overstock position, that the sales guys are not doing their job. So we've got a lot of stock there, we can't sell it, and the machine is not working for those reasons. So that is what we would call a functional failure. It's got absolutely nothing to do with the asset, but the machine is not working. But we'll be concentrating on the first three types of failure: the catastrophic, the predictive, and the proactive. So let's look at breakdown maintenance. Now, this was the primary type of maintenance, and I'm using it loosely here because there's nothing really maintaining going on there. But this was the primary type of maintenance that was followed up until probably shortly after the end of World War II. And the reasons for that was that in those days, machines were really quite simple. They were quite easy to fix. It didn't make a lot of sense to spend time and effort and money maintaining machines that could easily be repaired. And there was also not really a concept of global competition. So there weren't really any drivers to improve maintenance. In breakdown maintenance, you have 100% failure rates of catastrophic failures. Okay, so the first time we know something is wrong with the machine is when it's been reduced to a pile of smoking metal on the floor. Your downtime is 100% unscheduled downtime, just fixing and replacing components. It requires a large maintenance budget because you've got to buy all these new components, and your reliability or the reliability of the organization is poor and obviously quite unpredictable as well. Now, due to global competition and machines becoming more advanced, they realized that they had to improve maintenance. And so the next type of maintenance that was conceived was preventive maintenance. Now, preventive maintenance is a time-based maintenance. So we repair or replace at certain time intervals. Whether the work is needed or not, we still go in and we stop the machine and we pull it apart and we replace the bearings and change the oil, change the filters, whether it needs to be done or not. Now, the advantages of preventive maintenance is it reduces the number of failures, but not the severity of the failures. The failures that you have are still 100% catastrophic. You just have less of them because you are replacing some of those components that were about to fail. We're going to have a slightly lower maintenance budget, and I'll get you some comparison figures shortly. Because we have fewer failures taking place, we're going to have increased uptime, once again, due to fewer failures, and more planned downtime and less unplanned downtime. This should be a con there, by the way. Sorry, I missed that. The big disadvantage of preventive maintenance is the amount of wasted work that gets performed. And various studies in the industry have indicated that this figure is probably in the region of about 60% of maintenance work that is being done is being wasted. That's doing things like changing oil that doesn't need to be changed, greasing bearings that don't need to be greased, changing filters that don't need to be changed, and replacing components that don't need to be replaced. So typical type of maintenance for preventive maintenance is going to be things like changing oil, changing filters, greasing bearings, changing out bearings, switching out pumps, motors, gearbox, all done on a predetermined basis, whether needed or not. Now, at the advent of the jet age, when the Boeing 707 arrived on the scene, the airlines quickly realized, and the Federal Aviation Administration quickly realized, that the type of maintenance practices that were acceptable for a piston-engined airliner were just not good enough for a jet airliner, given the higher speeds and altitudes and the complexity of the turbine engines. So they looked at better ways of doing maintenance, and a new maintenance philosophy became dominant in industry, and that was called predictive maintenance. And predictive maintenance is designed to detect failures in the early stages by using condition monitoring tools. And this is where oil analysis comes in, vibration, infrared thermography, motor current analysis, and so on and so forth. So the idea of predictive maintenance is to reduce the severity of the failures. So we're no longer having catastrophic failures, but we are having failures in the sense that components have started wearing. We're not reducing the number of failures. All we're doing here is reducing the severity of the failure. We have a reduced maintenance budget because the repairs are cheaper now. I saw some stats from Caterpillar a while ago that said to replace a component once it has failed is going to cost 50% more in parts alone if you replace it before it fails compared to replacing it after a failure. And then we also have the advantage of increased uptime because our repairs are quicker. The cons of predictive maintenance are that it is still reactive in nature. It is still a firefighting strategy. We are running from fire to fire. We don't plan our maintenance activities. Our machines do that for us. So the typical type of work we would get in predictive maintenance are going to be doing things like taking samples, and we're going to be focusing on the where section of the oil analysis report. We will be doing vibration readings, looking for vibration that is induced by wear as opposed to vibration caused by something like misalignment or imbalance. We will be doing oil changes based on a problem. We will be replacing components when we detect a problem, when we detect wear taking place. So that is the type of maintenance activities we will be doing with predictive maintenance. And then finally, we get to proactive maintenance. Now, proactive maintenance is realizing that all wear has a cause of some description. And the theory is that if we can manage the causes of wear, then we won't have too much wear to worry about. So proactive maintenance has the advantage of reducing the severity of the failures and the number of failures, because we're getting to the root cause of the failure before the wear actually starts. So we are doing things like focusing on the condition of the lubricant, and we're focusing on contamination of the lubricant. We're going to be looking at the bottom half of the report that I put up earlier. And we have got the advantage of reduced maintenance budgets. Our repairs are fewer and cheaper to fix, increased uptime and reliability. A possible con of proactive maintenance is that it, and this is just experience, shows that it is quite difficult to manage. It does require a high degree of management. There is a culture shift that's required in the organization to get away from repairing things that are broken to, basically making sure stuff doesn't break. That's maintenance organizations exist to fix stuff that is broken. And if nothing's broken, they might see that there's not, they're of no use anymore. So it is a bit of a culture change that is required to get into a proactive maintenance situation. And to be fair, proactive maintenance cannot exist by itself. It has to be backed up with predictive maintenance, because there are things that cause a machine to fail that are just not detectable or are very difficult to detect. I'll give you an example. If you're just doing oil analysis in your organization, no other type of condition monitoring, if you have got a shaft misalignment, you are not going to pick that up with looking at the oil condition. You are not going to pick it up by looking at contamination. You will only pick it up once the machine starts wearing. So we have to back up our proactive maintenance with a predictive maintenance program. The type of work we'll be doing with proactive maintenance is going to be looking at the condition and contamination of the oil, checking oil levels are being maintained, changing oil only when we need to, changing filters when terminal pressure is reached, as opposed to changing them once a month or once every 3 months, greasing bearings using technology-assisted re-greasing such as ultrasonics, making sure that seals, breathers are in good condition, tank headspace is in good condition, doing things like filtering oil rather than changing it, depending on the type of contamination, making sure our machines are aligned and balanced, and then backing it up with a predictive program checking for machine wear. I'm just going to summarize those different philosophies, and I've got a couple of extra columns here, a cost ratio, a cost comparison. These figures come from the US Department of Energy. I think they're based on a coal-fired power station. And also looking at a human body parallel. So with breakdown maintenance, we wait until the asset fails before we do something. We're looking at 100% catastrophic failures. And the human body parallel is having a massive heart attack. The first time we know there's a problem is when we hit the floor. Moving on to preventive maintenance. This is scheduled or time-based maintenance. We have the advantage of reducing the number of failures, but not the severity. Our maintenance budget has now come down to about 75% of what it was based on a pure breakdown maintenance type of operation. Some would say you could even get a better reduction in your maintenance budget like that. We're not using oil analysis in either breakdown or preventive maintenance, or for that matter, any other type of condition monitoring tool. The human body parallel is like going in for open heart surgery every 5 years. So every 5 years you get wheeled into the operating theater. The cardiac surgeon opens you up, replaces the valves, puts in a couple of stents, does a couple of bypasses. Whether you need it or not, we just do that every 5 years. Predictive maintenance. Here we focus on the early detection of wear. We're looking at a reduction in the severity of the failures. So no longer catastrophic failures, but we have less severe failures. Our maintenance budget is now down to nearly half of what it was at a breakdown maintenance. We are focusing on the top parts of the oil analysis reports. That's the wear. And here we, as far as the human body goes, we are looking for problems with the heart. So once a year, you go to the doctor, get onto the treadmill and have an EKG. And when they find a problem with the heart, then they wheel you into the theater to do something about it. And then finally, proactive maintenance. Here we are addressing the root causes of the wear. So we are focusing on condition, contamination of the oil rather than wear taking place. We do need to back it up with wear monitoring, but this is the focus of our program. Our maintenance budget is now down to 15% of what breakdown maintenance costs. And as far as the human body goes, we are looking at the things which cause heart disease, such as blood pressure, smoking, cholesterol, weight, and so on and so forth. Just to give you an idea of some of the cost savings that can be achieved by condition-based oil changes rather than preventive or time-based oil changes. It stands to reason that machines operating in different conditions, the oil is going to last longer. Now, when you purchase in this case, a hydraulic excavator from an OEM, they've got absolutely no idea of what you're going to be using that machine for. So they are probably going to base their recommended oil drains on a more severe type of wear situation. But I think it's easy to see that if the machine is doing this type of work, there's absolutely no reason why the oil should not last for substantially longer than the oil in the machine on the right here. To give you an idea of the true costs of changing oil, this was information which came from a study done in 1999. So the numbers are 20 years old, 20 plus years old. It was done at a power station as well, and they looked at the true cost of changing oil. Now, this was to change 5 gallons or about 20 liters of oil. Parts and labor to change 20 liters of oil came to about $65 back in those days. And often that is the cost that is seen. But when you change oil, there's a lot more work that goes into it as well. Things such as paperwork, permits. You need to have this oil sitting in stock somewhere. You need more mechanics and fitters on site. If you're changing oil frequently, you need more foremen. You need a bigger HR department. You need a bigger payroll department. Generating purchase orders for all this new oil. There's a lot of hidden costs associated with just a simple oil change. There are some of those different things. And what they found was the hidden costs associated came to almost $1,000. So your true cost of changing oil is not the $65. It's actually much closer to $1,000. So for nothing else, there's a good reason to try to change the oil based on the condition of the lubricant rather than somebody told you to change it every 500 hours or once a year or whatever the case is. Now, which philosophy do you use on a machine? Obviously, there's different types of maintenance philosophies are more appropriate for different types of machines. The type of maintenance that is done on, say, an airliner is going to be very different to the type of maintenance that we do on a light bulb. And there are various different tools available out there for taking a machine and considering what type of maintenance philosophy is appropriate for that. I'm not going to get into that now, obviously, but I'm going to finish off with just looking at an example of a dripping tap. What maintenance options could we perform on a tap? So if you're practicing breakdown maintenance on a tap, that would work by waiting for the tap to drip, then replacing the washer. Quite simple. If we were going to practice preventive maintenance on a dripping tap, then we would replace the washer maybe once a year, once every 6 months, whatever we decide. Whether it needs it or not, we still go ahead and we replace the washer. That would be preventive maintenance. Predictive maintenance applied to a tap would be every month we stop the tap, we take the washer out, we test the elasticity, we measure the dimensions, we put it under a microscope, we see if it's got any scuffing or anything on it. And if there's a problem with the washer, then we go ahead and change it. That would be predictive maintenance. We're looking for problems, we're looking for wear associated with the tap washer. Our proactive maintenance would be to say, well, what causes the washer to fail? So we start doing some investigations. Maybe it's very hard water that's causing the elasticity of the washer to change. So then we put in a water softening plant just upstream of the tap. Maybe there's dirt in the water that's causing the washer to get scuffed. So we put in a filtration plant upstream of the tap. Maybe we found out that people are tightening the tap too hard. So we take the handle off and put a torque wrench on. That would be proactive maintenance. Now we still need to back it up with a predictive maintenance type of program. So every month we still need to take the washer out and check it for signs of wear. Now, I think we would all agree that certainly the last two philosophies would be a little bit extreme to apply to a dripping tap. Preventive maintenance, we might use that at the corporate headquarters, and we don't want customers walking up the path and seeing a dripping tap, so we might decide to replace the washer once a year. But I think most of us would practice breakdown maintenance in our homes when it comes to tap washers. So there is an appropriate maintenance philosophy for every type of machine. You just need to use a bit of work to go through a process to determine what that is. And once we have determined the correct maintenance philosophy, we can then go back and see where we are going to concentrate on our oil analysis report. And I'll just finish off with this slide. This is an examination of the costs of maintenance versus the cost of reliability. In a situation on the left here, we have got this blue curve is the cost of maintenance. That's how much money we're spending on maintenance. And the orange curve represents the cost of unreliability. So if we are practicing no maintenance spending, we're in a breakdown maintenance type of situation, we can expect our unreliability to be higher. The cost of unreliability is going to be high. Our total cost, that is the gray curve there, our total cost is going to be high. The other end of the scale here, we've got a situation where we're spending vast amounts of money keeping our machines working. They are very reliable, so the cost of unreliability is low. But because we are spending so much money on keeping the machines reliable, our total cost of ownership is going to be high. The sweet spot is somewhere in the middle, and this is what our jobs as reliability professionals is to do, is to try and find a sort of a sweet spot where we are not spending too much money on the maintenance, and yet we have machines that are generally pretty reliable, and the cost of them being down is not too high. Airlines would operate in this type of environment over here. They over-maintain their machines, whereas something like a little home cottage industry, like a seamstress who does sewing, okay, probably does no maintenance on the sewing machine, and when it breaks, then 100% of income stops until that fails. So that's where I'm going to finish off. If we have any questions, Jan will take him now.
Yeah. Thank you very much, Ashley. That was excellent. We have a question there from Liam Lawler. He says, asking, is oil sweetening a possible short-term fix to improve oil condition? And is it suitable for certain conditions, example, high air release?
Yes, I have seen oil sweetening done. It is difficult to do. Typically what's involved is getting the OEM in. They will come and take samples of the oil, test it in their laboratory, and come back with a drum of additive, which is then mixed back into your main oil tank. There is an element of risk there that whatever will, that it could go wrong. I would say from what I've seen, most of the time it seems to work, but I also have seen a case where it failed. And in fact, that case was due to air release. Was that the
example? Yeah, for example, air release.
Yes. Now that was actually a case where I saw it went wrong. The air release additive that they put in too much of the stuff, and that actually caused foaming to take place. It made it worse. But yes, it's definitely something that should be considered. When you have a very large volume of oil, which would be expensive to change. I would say going forward, one probably wants to be in a situation where instead of waiting to the oil to get to the point where it needs to be sweetened, that maybe on an annual basis you do a drain and replace of say 10% of the volume of the sump. You keep that up. You shouldn't get into the position where you need to sweeten the oil.
Okay, thank you very much. I hope Liam got an answer on that question. I think we'll finish up with there. Thank everybody for participating and joining this webinar. Thanks, Ashley, very much. If you have any questions, of course, you're more than welcome to contact Ashley, myself at TELLab to answer your questions. So on that note, I'd say thank you to everybody for joining, and hopefully you'll have a good day. Enjoy your day. Thank you.
Thank you, everybody.